All right, we've talked about different types. Okay, we talked about different types of nuclear decay last week. This is the last type that we're going to discuss, and it is dealing with stabilizing the nuclei by losing alpha particles. So as we're talking about stabilizing nuclei, we discussed earlier stabilizing the nuclei by a beta particle. We talked about electron capture. We talked about positron emission. This is the fourth type, alpha particles. An unstable nucleus that has an N to Z number that is much larger than 1 can decay by emitting an alpha particle. Remember that N to Z number was the number of protons and neutrons divided by the atomic number. The larger ones had more of a 1.5 to 1 ratio. The smaller elements had more of a 1 to 1 ratio. Okay. None of the elements that have atomic numbers greater than 83 and mass numbers greater than 209 have stable isotopes. So those are some of the bigger ones on the periodic table. Many of these unstable isotopes decay by alpha particle emission, getting rid of alpha particles. Alpha decay here, folks, is pretty easy to pick out. And as you're going to see when we're doing some of these types of nuclear equations that we're balancing, all right, you're going to see right here this 4,2 helium. That 4,2 helium is the alpha particle. So that is the alpha decay, if you see something like this. Now, this is a balanced equation of the release of an alpha particle, and this is stabilizing that nuclei. We'll talk about this next, but if you look, what's 238 minus 4? 234. What is 92 minus 2? 90. So, what is element TH? I'm not familiar with that. I'm going to guess thorium. Okay? But I'm not totally familiar with TH, so let me find it. It is thorium. Okay? So, the product of alpha decay of uranium-238 is thorium-234. And also we get rid of an alpha particle. Now, how did we know it was thorium? We looked at that 90. What is thorium on the periodic table? Has atomic number of 90. So take out your periodic tables. We're going to use those here when we're discussing. I gave you a worksheet. I gave you a worksheet that says working nuclear decay equations. All right, working nuclear decay equations. Okay. Don't want to be able to hit that, so I guess I got to come here to hit it. And this doesn't look exactly what you have in your hand because you have the symbol with the X and the A and the Z up at the top, meaning the mass number for A. The Z is the atomic number. So, the very first one on your page says the alpha decay of uranium-238, the most common isotope of uranium. Now that's the one that I just showed you. I guess I didn't realize that that was the one that I had on my slide, but uranium is U. 238. What is the atomic number of uranium? 92, right? We just dealt with that. So 238, 92 is the bottom number. Now, when it is undergoing alpha decay, I told you we're going to have, geez, my board needs a little work. Why is this board crazy? Okay. Nonetheless, we're going to have helium, 4/2. All right, we're just going to have to go with it, I guess, here, people. We're not going with that. Yeah, but I'm not going to take that time. We're just going to go here, and we'll go here. All right, this board's going to tick me off here. All right, here we go with the alpha decay. This is probably going to be the same thing, isn't it? Uranium. Oh, it's not even going to work. All right.